All right, black holes. Black holes are a fun topic because most people don't really know anything about them, or the things they know are something they see in like Interstellar or something. They're some of the most complicated, yet some of the most simple objects in the universe, and are extremely interesting, and not very well understood, even by scientists in many aspects. To start, I'm just going to quickly give a rundown of what I'm doing, and to justify my existence here. I do astrophysics, like that's my degree. I'm going into my last year of it, and so I'm somewhat qualified to speak on this. The information isn't just coming out of my ass. I spent a while researching this. It came mostly from a textbook, the textbook that I used for my astronomy courses, called Carroll and Osley. There will be some math here, but it'll just be whatever you could do in like grade 9 science or physics. So it's not going to be too bad. The math, the calculus that is nice to know. It's insightful, but we don't need it to understand what's going on for a good, for a fun exercise here, and for people to get a good understanding of even the complicated physics going on with black holes. So the first thing I'm going to start with is one of the most interesting things I learned in my astronomy courses, and that is what is called a Seyfert galaxy. You may have heard many names for these kinds of objects: quasars, blazars, radio galaxies, or Seyfert galaxies. The idea is that in the early 1900s, folks like Seyfert noticed that some galaxies had really, really bright stuff coming from the centers of them. These centers were so bright that they eclipsed the entire rest of the galaxy. They were brighter than all the other hundreds of thousands of stars in the galaxy combined. We have cataloged these into many different categories today. Only less than 1% of galaxies have this, but there are still thousands that have been measured. And what we see in different ones is different types of emission. We see some emitting in radio, some emitting in X-ray, some are brighter than others, some are fluctuating, and they have been kind of categorized in all these different groups and given all these different names. And the question is, what are these things? What's causing this dominating presence in the center of some of these galaxies? Why is it only in some galaxies and not in others? So this thing is called an active galactic nuclei, and like I said, makes up less than 1% of galaxies, like 0.1%. And you may have heard these terms when people talking about astronomy, of quasars and blazars. They're just different names for these different types of objects. It means slightly different things. So a blazar, for example, changes luminosity very rapidly. It could change as much as 30% of its brightness in a day, and you can notice the change within an hour, which is crazy because this thing is billions, hundreds of millions of times brighter than the sun, and it can change by this much over the course of a day. And the main question that astronomers were wondering when first looking at these things, are all these different types of objects, quasars, blazars, radio galaxies, are they different, or are they the same thing, just looking a bit different? And we'll come back to this, but I want us to keep this in mind. And I'm going to talk about now some of the properties of them that we can determine from basic principles of physics. So the first thing we can do is we can approximate the size of the object that's causing this. And from here, we go into the math. I guess I'll mention, this slide and also the accompanying math thing that I made will be available in the resources chat along with the recording. So I'm going to quickly go through how we can roughly determine the radius of the object that's causing this massive brightness. So the idea here is that for something like a blazar, we can see the luminosity changing rapidly. But the luminosity change isn't instantaneous. The idea is that we see the luminosity change at the center of the object, then at the edge of the object at different times, and so the change in luminosity is smeared over a certain amount of time. We can use this to find out the approximate size of the object, because if we know how spaced apart we're seeing from the center to the outside, we can then determine what that distance is. We can set this up very simply by using basic principles of physics. The velocity is the distance over time. By substituting in the speed of light, because we're having light come towards us, the radius, the distance from the center to the edge of the object, and then the difference in time in noticing the luminosity changes. We can isolate for the size of the object, and when we plug in the speed of light and the time scale of about an hour, that's what we see for the smearing of the brightness changes, we get this approximate radius for these kinds of objects, which is about 7 times the average distance from the Earth to the Sun. So whatever's causing this isn't a third of the size of the galaxy. It's a very, very small object in the grand scheme of things. Next, we can find its minimum mass. And we can do this by using the properties of stars. So quickly, I'm going to jump into what a star is and talk about that, because, as you may know, black holes come from giant stars that have died. So, the basic thing to know about stars is that they're mostly hydrogen. Most of the universe is hydrogen. And if you have a large enough collection of hydrogen gas, and there's enough gravity, it'll pull itself together into a nice sphere. And once there's enough pressure at the center, and once it reaches 10 million degrees, it'll start fusing hydrogen, and that is the star burning. It has its hydrogen from the initial gas cloud, and it burns that over the course of its life. The life of our sun, which is a relatively small star, is about 10 billion years. Stars, the main thing that keeps them the way that they are is called hydrostatic equilibrium. You have gravity pulling the star in, but it doesn't just get contracted into nothing. You also have the fusion pushing energy outwards, and the star doesn't just fall apart because of the gravity pushing in. These two forces, the outwards force from the fusion and other things, and the inwards force of gravity, balance each other. And that's what keeps stars from just falling apart or contracting into nothing. But eventually, you will lose this balance once you've burned all the hydrogen. For our sun, once the hydrogen is burned, the outer layers will kind of just fall off, and it will be left is an inert core. It's called a white dwarf. But for larger stars, it gets more interesting. But it's the idea of hydrostatic equilibrium that we're going to use to figure out the mass of the thing that is causing the active galactic nuclei. Going back to the math, you'll have to take a couple things for granted because we cannot go through the calculus to determine these things. But the idea here is that if we assume that whatever is causing this massive brightness at the center of these galaxies is something like a star, if it's something like a star, if it's just a bunch of hydrogen, and it's large, then we can say that the outwards force is largely from the light going physically outwards. In large stars, you see this at their outer edges, where it's the light caused by the reactions and other things moving outwards that is the main outwards force. And then, of course, gravity is the inwards force. When you have a object like this, and it is really bright, the brightness means that there's more light, which means it has a higher outwards force. And the mass means there's more gravity, which means a higher inwards force. So, to balance a certain luminosity of outwards force, you need a certain mass. Or in other words, for an object of a given mass, there's a maximum luminosity that it can have, or else it would just fall apart. This is called the Eddington limit, and it's pretty important. The course derivation I can't get to now, but what the important thing is that the luminosity of an object is directly related to its mass and just a bunch of constants in front. We have measured the brightness of these objects, and they're on the order of something like 5 times 10 to the 39 watts, which is about 1 billion times brighter than the sun. What we get is that the mass, the minimum mass, because it could always have more mass to contain this luminosity, but the absolute minimum mass that this object can have is about 3.3 times 10 to the 8 solar masses. That is 300 million times the mass of the sun. So there's some object within 7 of Earth's radiuses of the sun with at least this much mass. What the hell could that be? Of course, you could probably guess what that's going to be based on the topic of this lecture, but that is an interesting application. And now I want to finish the talk of stars, because we'll circle back to this idea once we figure out a bit more about black holes, because, spoiler alert, it's black holes. In a small star, I mentioned, like our sun, the outer layers of the star will just kind of fall off, and we'll be left with an inert core called the white dwarf. But with a large star, it's a bit different. When the hydrogen runs out, a bunch of the outer layers kind of just fall off, like with our sun. But what will happen in these large stars is we'll start burning the helium and the oxygen and the neon, the sodium, magnesium, and silicon, as these are the things that were formed by fusing the hydrogen, and then they get fused themselves. The problem is that burning these does not generate as much energy as the hydrogen. And so then each layer is getting burned faster and faster to maintain the energy. So the hydrogen layer is going to take millions of years. For a large star, it burns a lot faster than a small star, actually, just because of its size. The carbon layer will take like 300 years. And then the silicon layer, the second to last one, will take 2 days. Eventually, once you've burnt the silicon layer, you have a core fill up with iron. Iron is the first element to be energy negative to fuse. So what this means is that it is being fused in the core, but it is taking energy to do that. So the core is losing energy. On top of this, the properties of the core now are causing heavy atoms to break down, and they're causing electrons to be captured. The breakdown of the heavy atoms, the capturing of the electrons, and the energy negative fusion of iron is causing the outwards pressure of the star to massively go down, meaning that eventually gravity takes over and it's a runaway effect. In 10 seconds, boom, the entire core collapses. But what's interesting is it's only the core that collapses. The outer layers just kind of sit there. Eventually, when the core is collapsing because gravity has won, it's collapsing so far that the particles get too close to each other, and then it kind of bounces back a bit. When it bounces back, it shoots shock waves out, which push the outer layers that have been just kind of hanging above. The shock wave pushes them out, and that's the explosion of the supernova. This will happen for stars that are like 8 times the mass of the sun. And if they're something like 10 times the mass of the sun, the bounce back after the particles get too close will stay, and it'll create something called a neutron star. But if it is large enough, like 25 times the mass of the sun, it will create a black hole because the gravity will still win even after it bounces back. And so that creates a black hole. And now we're going to go into the second mathy portion here, where we're going to talk about the definition or the initial theoretical motivation for what a black hole is. So again, if you've taken grade 11 physics, you'll recognize this. If not, you will see it. The first idea is that if you have an object orbiting a star, it'll have a certain gravitational potential energy that it feels from it. You feel the gravity on you, and it is described by this formula. G is a constant, R is the distance between you and the star, the big M is the mass of the star, and the small m is your mass. Then, we can write the kinetic energy of U as 1/2 times your mass times your velocity squared. That is another basic principle of physics. The total energy that you possess is the kinetic energy plus the potential energy, and so you just add those two quantities together, and this is your equation. So the idea here is that on the Earth, there's a potential energy that you feel from it, and what you'll notice is that if R is greater, then that means that this number will be smaller, and if R is less, then it'll be bigger. Now, what we're going to do is we're going to set the object really far away from the star, where we assume that it's not feeling anything from the star. What happens is that we set the potential to be 0, but since there's no effects that have been played on it yet, we're also going to set the velocity to 0. Because of this, the initial energy of the object must be 0. And then, if it starts moving towards the star, its energy must remain 0 at all times. By setting E equals to 0 and then moving stuff around, we can get this direct relation between the kinetic and potential energies, solve for the velocity, and you get this equation. What this can be interpreted as is an escape velocity. So on the Earth, if you want to escape Earth's gravitational pull, you have to move at about 11 kilometers per second, and that's created by this equation. But now, here's the idea that motivated black holes. What if the escape velocity is the speed of light? That is the fastest possible speed you can travel. And so what if you had an object that caused that? We can rearrange this equation in terms of r to get the radius of such an object. What this equation is telling you is that if you have an object of mass m contained within this radius, it will have an escape velocity at the speed of light. And so if you have even more mass, that means that light can't even escape. This is called a Schwarzschild radius. For the sun, it's about 3 kilometers. So if you took the entire mass of the sun, put it down into a 3-kilometer ball, it would be a black hole. And this is the motivating thing for the name black hole. Light can't escape from it because of the high gravity. It cannot reach the escape velocity. And so you don't see anything because there's no light bouncing off it, and therefore you just see blackness. So it's a black hole. And so those are the main ideas to motivate what a black hole is. And actually fairly simple physics to get there. The Schwarzschild radius, it defines at what radius light can no longer escape the black hole. And so that is called like the surface of the black hole, or the singularity. Singularity, point of no return. Once light hits it, it cannot come out. So you can't see anything beyond the singularity. A property of how much shit can a black hole keep in it? As much. It can eat anything and everything. If stuff flies into it, it will just keep eating it. There's no limit. Yeah. But I'll talk about some interesting things. I'll bring it up in a second. For now, properties of a black hole. I mentioned at the beginning of the lecture that black holes are both the most complicated and the simplest objects in the universe. They can be defined by three things: the mass, the angular momentum, and the electric charge. If you know these three things, then that is all that you need to know everything about a black hole. The Earth, for example, you would need to know the mass and the radius and all the different things that are in it, the composition of everything, the composition at every single point. It would be an infinite number of parameters to define what the Earth is. But a black hole with these three values defines everything that it is. This principle is called the black holes having no hair. I don't know why it's called that, but the idea is that you might have a complicated star where its stuff is randomly distributed in it, and it's impossible to define exactly what it is, but all those imperfections are radiated away, and you have a perfect sphere defined by just these three things: its rotation, its mass, and its charge. Oops. Now, we talked about black holes eating things. You might wonder, why doesn't a black hole just eat everything? When you see pictures of black holes, like, go back, here, this is a picture of a black hole thing, and you see stuff around it. Why isn't it just eating all of that stuff, right? Well, the reason why is actually the same reason why the Earth doesn't fall into the sun. Despite the fact that there's a large gravitational pull, the angular momentum of the object orbiting is maintained, and so it'll just rotate around it. I'd love to go through the math, and if anyone's ever interested, I can do that. But it's this idea where angular momentum is conserved, and because of that, if you move too close to the star or the black hole or whatever you're orbiting around, your speed gets higher, so then you fall around it. And so the same reason that the Earth doesn't fall into the sun, or the moon doesn't fall into the Earth, or the International Space Station doesn't fall into the Earth, things don't just fall into the black hole unless they're pointed directly at it when they fall into it. And so yes, a black hole can eat anything, but it'll also have stuff just hanging out around it because it will be coming at it at an angle, and it'll kind of just spin around it. Another thing you see in these pictures, you see in this one, and also, I like this pretty one here, there's these jets coming off the top and the bottom. And you're like, what the hell is that? That stuff is going outwards, and these aren't actually fully known. What causes this, why this happens, because it doesn't really make any sense. Why is stuff being shot away from the black hole? The idea is that it's caused by the rotation. Stuff gets sucked up and shot out. It might be due to a certain thing called frame dragging in space-time, but the main idea is that it's because of the rotation of the black hole that stuff gets shot out either way. And now with this knowledge, we can return to what we talked about at the beginning. Some folks have arrived since then, so I'll give a quick recap. Active galactic nuclei are a thing that I'm talking about. At the centers of some galaxies, like 1 in 1,000 galaxies, there is an active center that's brightness is brighter than the entire rest of the galaxy combined, sometimes several times brighter. They have all these different properties, and in the beginning, no one really knew if this was a bunch of different things or different types of the same thing. We now know that it is all different types of the same thing, and that same thing is a supermassive black hole. The reason why it caused these measurements, and what all these different types of things are, is that you have the accretion disk around it and the jets shooting out, and the different types of objects that you see, quasar, blazar, radio galaxy, Seyfert galaxy, is simply the angle that you look at it at. So a blazar might be looking at the jets, while other objects will be looking at the clouds or the dust. So it is all different types of the exact same thing. And that's what's actually kind of neat about this. is that people hypothesize that it could be different things, or that it's really complicated, but it's actually a really simple system. All these galaxies have a supermassive black hole at the center, and it's because it's accreting material. Stuff is rotating around it, and stuff is hitting it, that we see these different effects. The jets come out, and the clouds are created around it, and it's simply the angle that you look at that causes a different type of measurements. Now, we're going to go into the special relativity effects here. Because if you've ever seen Interstellar, you know about the time dilation stuff with going around black holes, and we're going to delve into that a bit because that's kind of the most exciting and difficult stuff. Yeah, no talking during class, okay? And no passing notes. Anyways, back to the stuff. Velocities are relative. This is a universal principle. You're driving in a car and you see someone standing on the side of the street. To you, they're moving backwards. To them, you're moving forwards. And so depending on where you are, depending on if you're moving or if you're not, you will see things at different velocities. And so all velocities are relative. You can't just say, I'm moving forward in my car and that's objective, because to someone else who's moving faster, you're moving backwards. But the kink in this plan that caused a bunch of problems that Einstein solved is that the speed of light is the highest possible speed, and it can't be changed. If light is moving at a certain speed, it will not move a different speed. And so what happens because of this? Things need to change to make up for this effect, because what, instead of driving in a car and seeing someone stand on the side of the street, you're sitting on a beam of light and you see someone stand on the side of the street. You both need to agree that you're moving at the speed of light, when before you were in a car, you disagreed on your speed. So what happens? Well, there's two effects. Time dilation. When you're in the car or you're on the light traveling, time moves slower for you. You saw this in Interstellar, where the people orbiting the black hole had time going slower for them, so when they came back to Earth, everyone aged like 80 years. The second thing is length contraction. When you're moving on the light, the distances are literally smaller for you, and that also helps make up the difference. What's interesting and relevant for us is that gravity causes the same thing. This is from Einstein's special relativity. The large space-time warping around a black hole also causes the time dilation and length contraction stuff. And this is what we saw in Interstellar. People orbiting the black hole had time moving slower for them. And so now, with these concepts in mind, let's see what it's like to jump into a black hole. The first thing we're going to talk about is someone else jumping into a black hole and what we would see. So, the gravity at the singularity of a black hole is infinite. Therefore, time dilation is infinite. So when you touch a black hole, time stops. In other words, a black hole is a frozen star. The surface of the star that created the black hole is effectively imprinted on it. You can't see it because no light's coming out, but the surface of the star is forever imprinted on the outside of the black hole because it'll never reach the surface. Now suppose that someone jumps into the black hole and they have a flashlight, and what they're doing is exactly every second, they're shooting light back at you. And you're going to measure the time between these flashes and look at the flashes. What happens is, as they get closer to the black hole, the gravity will increase and their time dilation will increase. To them, they're pressing it every second, but to you, you see the flashes being further and further apart. What we also see is that the light gets redshifted and gets dimmer. I guess I have to explain redshift now. If you know when you have like a car driving past you and it goes like meow, meow, and the pitch goes down of the sound of the car, that is the sound of the car being blue shifted. The same thing will happen with the light, whereas it's moving, it has to travel further to get to you, and it has to work against the gravity. It'll get more red. And it'll also get dimmer because it's effectively traveling a further distance. Meow. Meow. What was that? Was that a good sound, Herx? I've been practicing. Turn that into a soundboard sound. Meow. Meow. You can't see it, but I'm like moving my arm like it's the car that's moving. Anywho, the light from the person jumping into the black hole. It's getting further and further apart, and it's getting dimmer, and it's getting redder. Until eventually, we don't see it. They're getting infinitely far apart and infinitely dim. The person who jumped in is stuck in place and stuck in time. Okay, so question about the Hawking radiation. I'll talk about that briefly at the end. I don't have a slide on it because I don't know much about it and I haven't done the math, but I can talk about that briefly. But before we get to that, what if we jumped into the black hole and we're the ones holding the flashlight and shooting it back? The picture on the slide is the best diagram I've seen for this, but it was in the textbook I was literally reading and I couldn't find a PDF, so you get a picture. Okay, so when we jump in, time is passing normally for us. And every second, we click our flashlight and shoot light back. And that's it for the first little while. Until eventually, you feel yourself get stretched. When you're getting close enough to the black hole, there is a gravity gradient where the gravity is far higher at your feet than your head. And also, since the black hole is a sphere, there's a slight angle discrepancy where you see this one's going towards the right, this one's going to the left. So what happens is you get stretched in the vertical sense and you get compressed in the horizontal sense. And you will get ripped apart and also squished. And this is actually called spaghettification because astronomers cannot be trusted with naming things. And you can kind of see it in the picture I took here that they're claiming that the compression is more severe. Regardless, you're dead. And you're dead hundreds of kilometers from the event horizon. But what if you didn't die? What if you are, Mr. Fantastic and you can stretch and you're fine? What would you see? Well, you would never see the singularity. You'd never see the black hole because no light is going to bounce off to get to you. And you're also not going to see something that fell in before you. So if you're chasing after your friend who fell in, you will not see them. But you can see the things that fell in after you because the light will reach you. And now, I've heard this actually many times, and I believed this for a while until I started reading for this, that you would see the whole universe unfold. It's true that time would stop for you, and the whole universe would unfold while you're falling into the black hole. But you wouldn't see it, because there wouldn't be time for all of the light to get to you. So, yes, you would get ripped up instantly when you fell in, but there wouldn't even be this cute idea of getting to watch the universe unfold. It would unfold while you're getting sucked in, but that's about it. And yeah, the Interstellar, you would not be able to talk to your past self in the bookshelf. But neat idea. I know, right? Okay, so there was a question of the Hawking radiation. That wasn't the words used, but that's what it's called. Stephen Hawking found out that black holes will slowly die. They'll slowly radiate themselves away. I was going to talk about this, but I ran out of time. The math is complicated and not fully understood. But the idea is that you will have particles that hit the black hole, particles on the edge of the black hole that will break into two pairs. One will go in and one will shoot out. And so this is a very random thing where you'll just have this quantum effect of these particles breaking into two, and then one goes in, one goes out. And over really, really long time scales, the black hole will radiate to nothing. And so the really depressing narrative of the universe based on cosmology is that everything will eventually spread apart because of the expansion of the universe. All the stars will eventually die because everything's so spread apart you can't make more. There'll only be black holes left. They'll eat everything, and the black holes themselves will die, and they'll just be radiation. Yay. Yeah, the black hole in Interstellar. Kip Thorne is a real astronomer who was in charge of the science of the show, and so when they rendered it, it looked proper. So you see this look of the black hole, and I guess I can talk about this. What the hell are we looking at, right? So the black hole, where was it? Here, this is an actual picture of the black hole. This is the one at the center of our galaxy, actually. It's called Sagittarius A. And you see the red around it, and that's from the accretion disk that we were talking about, of the stuff accreting around it. But then why is it that when we look at the picture of the black hole, we see stuff on the back? Why is it like, isn't it just a disk that goes around? Why is there a second disk? what you're seeing is the back of the disk. That light will fall into the black hole, but a light that barely misses the black hole and goes around will curve around the black hole and get to us. So what you see on the top and bottom here is the back of the accretion disk. And so that, yeah, to my knowledge, that was all calculated properly, and all the physics of like the planets and all that stuff was done properly, and the time dilation was calculated properly as well, which I think is why the movie ended up kind of being a bit goofy, that they had to make the planets work in certain ways so that the gravity would work. I don't know. I don't remember. This is all the material I have. I end at jumping into the black hole. If anyone has questions about black holes or otherwise in astronomy, go ahead. Interstellar is pretty accurate in the depiction of the black hole. There's lots of stuff that's kind of nonsense, and I'll have to watch it again to look at the planets now that I do planetary science. But yeah, they published a paper on like the calculations for rendering the black hole, because I think it was the most sophisticated rendering of a black hole that's ever been done, and it was done properly. You can pet a black hole, but only once. I think that's the right answer. What happens if a black hole sucks a black hole? It becomes a bigger black hole. They just become one, and they'll create something called gravitational waves. You also get this when the black hole's formed. And that was predicted by Einstein, and it was found at a place in the States called LIGO in 2016, and they got a Nobel Prize for it. Like water, I don't know the actual exact dynamics of it, but I'm pretty sure that like one just kind of sucks off the other, like the larger one. Yeah, you'd have to look up. There's definitely simulations of it, but that's something I didn't look into for this. I was going to, but didn't have time. Yeah, Interstellar is pretty cool because like they put good effort into it to make it legit. Wormholes. I can do wormholes at some point. That the problem when we get into stuff like that is the math. Because I was able to break down the basic stuff of the black holes into just, high school math. But wormholes, absolutely not. Because once you get into the curvature of space-time, this is courses I haven't even taken yet. Special relativity. Courses I won't be taking. But I can maybe do an interesting course, like a lecture on that kind of stuff, on these more, not like pseudoscience or sci-fi, but like this stuff that's so crazy but actually might exist, because the wormholes is like a theoretical calculated thing. It's not something that anyone's ever like measured, but it's a calculated thing. It's in my textbook. I skipped over the section on it. Stars, I don't know, I guess you missed, I briefly talked about stars here, and you can look at it in the slides or watch the recording. It was a basic thing. But I can do a whole thing on stars because I skipped a whole lot, and I could talk about, for example, the life cycle of our sun, what's going to happen, because it's not going to explode. It's going to become a white dwarf. The outer layers will shed off, destroy the Earth, and then it'll just have a white little core behind. Exactly. Shining, shimmering, splendid. Tell me, princess, now when did you last let your heart decide? Duck, would you like infinite bacon but no games, or games, unlimited games but no games? What? Infinite bacon or games, unlimited games but no bacon? Like, would I choose games or bacon? Is that the question? I choose games because I think bacon's like really specific, and so you could find something that's close enough, right? Yeah, I should have assigned watch Interstellar. We could have coordinated, done movie night Interstellar, and then had this. But maybe we can do that for the next movie night. Talk to Sin Eater. That'd be good. Now that we have some knowledge of black holes and time dilation, Because when I watched Interstellar, I remember I watched it in my physics class in grade 11, and everyone was confused, but I wasn't, because I spent my time on YouTube and shit learning about time dilation. And so that part was easy to me, so everything else I was able to pick up while watching. Well, they had to also pick up that stuff. So that's all it is that once you have the basic knowledge, you've heard of these concepts before, you can make up the rest while you watch. And so it'll be a better watch, I think, with the basic knowledge that we have now. That time dilation is a thing you'll feel around a black hole. And so then everything else kind of falls into place. If you haven't heard about it before, then you're like, what the heck's going on? What if a black hole the size of my finger opens up? Who did it? There was a YouTube video. Kurzgesagt? I think they did one where they talked about it. And like, yeah, I remember watching that. The problem, okay, because I think they kind of tackle this in the video, but the main thing is like, how is a black hole being formed? Because for something the size of your finger, that would have to be an object, I don't know, the size of a country. And so did that exist beforehand? And if so, the creation of the black hole will probably have enough, damage to destroy the Earth on its own. Isn't science mainly hypothetical at first? Well, yeah. I mean, black holes were theoretical. Like, the first thing was what I talked about here, that what if we take the escape velocity to be the speed of light? Then everyone was like, hey, this object could exist, and we've only gotten a picture of it a couple years ago. You come up with a theory and then go on to try and prove it. Not exactly. The orthodox scientific method that people go by is that you get data, and then you fit a model to it that predicts things, and then you see if you predicted those things. If you didn't, you tune the model. And so yeah, black holes were a theoretical prediction that maybe this thing exists, but there wasn't a theory behind it. And then people were able to measure stuff like the active galactic nuclei and other things and said, black holes are a thing, these are what they are, and now we have pictures of them. How do you gain data for something you observe for the first time? Well, that's the thing. The thing that you find for the first time comes from the data. I mean, yeah, black holes were predicted before they were found, obviously. But in astronomy, you might get data and then find something. So quasars were first discovered because, and the active galactic nuclei are a perfect example. They were discovered because people were looking at the sky and found weird data, and then they fit a model to it. And then it predicted other things. And now we have this all-encompassing model of the active galactic nuclei. That we've measured some of them, we measured more of them, and we found something that fits all of them. So any new one we find, we know exactly what's going on. And that's how the scientific method worked for those. And so yeah, you can have stuff that's theoretically predicted, like the wormholes. But no one's ever seen one. And so everyone's like, yeah, I guess they could exist, but we're not gonna do anything with that. Yeah, I'll give another minute if there's any other questions. I hope y'all's enjoyed the lecture. Explain how the solar system works. In what sense? I guess I can do a lecture on that. But if you do have a specific question, I can answer it, because that I do know. Sure, I'll give you a minute. I've got nothing but time. I'm falling into a black hole, so time's infinite. Thanks you, Herx, for letting me do this, creating all the roles and everything. We gotta set up more talks. I'm willing to let anyone, they don't have to be a mod or anything, do a talk. Just contact me. And we'll set that up. Talk about anything. Talk about, like, I'm joking, but I'll do it. A thing on how, a Riz tutorial. Like, talk about anything, and it'll be fun. I'll do the Riz tutorial. If people are into that, that'll be funny. I'll get my girlfriend to sign off on it. The first minutes of the universe's beginning. Oh boy, cosmology. I do planetary science, but yeah, I actually do know this. My current research is in cosmology. So the universe, everything was in one place, and then suddenly it was in many places. And that's the Big Bang. What first happened was it was really hot. It was like a giant soup. It was opaque, and nothing was able to form because it was too hot. Then it cooled down very rapidly, and once it cooled down enough, you were able to create subatomic particles. You were able to create the quarks and the electrons and the photons. Then once it cooled down even more, you're able to combine the quarks together to create protons and neutrons. Then once it's cooled even further, you're able to create the hydrogen and the helium and all of that. And then it became transparent, and so then there is light. And so then what we actually get, cosmic microwave background, this is called the CMB. It's the most important thing in cosmology, talk about the early universe. The first moment that their light could could go through the universe, because it was now cool enough that light could actually go through things without getting just absorbed, is this moment, and we have the radiation from it. And so this is the earliest picture of the universe, and the red is higher density and the blue is less density, and this became the structure of where all the galaxies are.